Hi, it's Ryan again, and today we're going to be talking about section 5.1, which is about the area that falls between two curves. It's one of the fundamental applications of integration. So to give you a picture of what I mean by that, consider that you have two curves f and g. Say a curve f of x and a curve g of x. And let's suppose also that we know a beginning point and an end point that we're concerned about here. So let's say that we're looking at the area that falls between x equals a and x equals b. Okay, so the basic question is, having defined a region like this, what's the area? So if we call this region in the interior A, the basic question is, what is the area of A? So the basic idea of integral calculus goes all the way back to Archimedes. And the essential idea is that I can calculate the area of something or the volume of something by chopping it up into little pieces, approximating the area of those pieces, and then adding them all up again. And that after I do that process of addition, I've got a reasonable approximation of the object that I chopped up. So you would have seen this when you saw the definition of integration. So I'm just going to briefly remind you what the central moves are, because the intuition for how integration works is going to underlie a lot of the techniques that we're going to be doing over the next couple of weeks. So the basic setup for integral calculus is you have an object. So you start with some object. And by object, what I mean is a region or a solid, some kind of geometric object in 2 or 3 dimensions. You cut that object into small pieces. Then you find the area of each piece, and then you add up the small areas. Now the idea here is that when I say small, I mean infinitesimally small. So there's limits going on in the background here. But we can at least write down the basic approximation that gives rise to all the formulas without having to work with taking limits or calculating anything with calculus. So let's go back to our original picture again. If I had the curve f, and I had the curve g, and I know that I want to be computing the area in here, the way I'm going to do that is I'm going to try to come up with what I usually call a typical rectangle. So I'm going to try to find a typical rectangle. That is, if I was trying to slice this thing up into pieces, each slice would look like a rectangle if we looked closely enough. So in this problem, the typical rectangle is going to look something like this. So you're going to have sort of a rectangular looking object, and the height of this object and the width of this object can be used to find the area of that object. So if we call this object, say, I don't know, A1, well, A1 is almost a rectangle, as long as we keep our widths skinny enough. And so I can compute its area just by doing base times height. So knowing that I'm working with base times height, I just need to write down what that is. So in the x direction, or I should say in the width direction, I'm going to call this delta x wide. So you can think about delta x as representing a small amount in the x direction. So whatever delta x is, typically we think of it as small. The height of this rectangle, well, the top of the rectangle is at f of x, and the bottom of the rectangle is at g of x. So we think about this point up here as being located at some point called f of xi. So this point right here on the x-axis is xi. That's where the rectangle is located. The location of the curve f over xi is given by the height f of xi. And the location of the curve on, or the point on g of x is going to be given by g of xi. So if I want to compute the height of this rectangle, all I need to do is take the difference of the top and the bottom. And that difference of heights is going to tell me how far it is from here to here. This is how you calculate the distance between 2 points, is you just subtract. So the distance between these two y values is their difference. So if I want to write down an expression for that, I could write down f of xi minus g of xi. So the height of the rectangle is given by the difference between the top and the bottom, and that means that the area of this little skinny rectangle, so the area should be equal to f of xi minus g of xi, because that's the height, times delta x, because that's the width. So this particular rectangle, if I had a point xi that I was given, I could calculate the top and bottom of the rectangle, I could calculate the width if I was given that, and the area would just be base times height. So how does this look when we want to estimate an area instead of just writing down a typical rectangle? Well, I could make lots of rectangles. So if we're looking at the same region, I could chop this into lots of rectangles. And the reason that I'm thinking about them as rectangles, even though the tops and bottoms are curved, is as long as I'm looking closely enough, these lines here are always going to end up looking something like straight lines. And for a skinny enough rectangle, it really doesn't matter how steep or flat the rectangle is at the top or bottom, because the rectangle is so skinny that the height dictates what the area is more than the width does. So the idea of looking closely or small, like infinitesimally, that's sort of the basic move of calculus. Okay, so each one of these rectangles has an area associated with it. So if we called, say, a given rectangle in here, I'm just going to name this. This rectangle right here is A3, and this rectangle here is A4. And so the area of the region is going to be about equal to the area of A1 plus the area of A2 up to the last rectangle that I've made. So the one at the end here we just call AN. And it's approximately equal because, of course, I'm thinking of these as rectangles and not as regions that have curved or slanted tops and bottoms. So it's not going to be exact. So it's still going to give me an idea of what the summation formula should be, because as long as I choose delta x to be the same for every rectangle, so delta x, delta x, delta x, delta x, then the formula for this is going to be equal to the sum from I equals 1 to n of ai, but each one of those we're thinking of as a rectangle with the same base. So this is the sum from I equals 1 to n of f of xi minus g of xi, that is the height of that particular rectangle, times the width of that particular rectangle, which is delta x. So each individual rectangle has a height and a width, but the widths are all the same. And my approximation is going to get better as delta x gets smaller and smaller and smaller. So this is the basis for the area between two curves formula. So now what I want to do is I think to myself, okay, well, the next step should be if the area is about equal to the sum of xi minus g of xi times delta x, how about we let delta x get small? Okay? And this is where the actual formula comes from. So the area between f and g, in the case where f is always above g, when f is greater than or equal to g, is going to be equal to the sum from I equals 1 to n of f of xi minus g of xi. That is the height of a given rectangle. So times the width of that given rectangle. And now we're going to play the calculus move, which is to let delta x go to 0. We're going to take a limit. So if we let delta x tend towards 0, which really means we're also letting the number of rectangles increase. The more rectangles we've got, the more accurate our approximation is. So at the same time, we're letting n go to infinity. Then we get the integral version of the formula, which says that the area is actually equal to the integral from a to b of f of xi, not xi anymore, we took a limit, f of x minus g of x dx. And so this is the area formula. And you can see that the structure is exactly the same. dx we think of as being a little tiny infinitesimal width, and the height of our infinitesimally wide rectangle is f of x minus g of x. Now the reason that we need f to be bigger than g is because we need the tops of the rectangles to always be given by f and the bottoms of the rectangles to always be given by g in order for this formula to make sense. So here's a more formal statement of the theorem. So the area between f and g, so this is a theorem. The area of the region, I'm writing this out because we're going to use there's some language in here that I want to talk about. Of the region bounded by curves y is equal to f of x, y is equal to g of x is equal to a, x is equal to b, where f is greater than or equal to g on the interval from a to b, is given by a equals the integral from a to b, f of x minus g of x dx. So what I mean by f is bigger than g is that for any x inside the interval from a to b, f of x is bigger than g of x. So they can touch, they could be equal, but f always has to dictate the top of the rectangle. All right, so that's the basic setup. The thing that you need to know most of all is this picture. So here's what your takeaway should be. You have a curve f of x, you have a curve g of x, you have a region that you're interested in investigating from x equals a to x equals b. As long as you have this setup, you've got a region that you can chop into rectangles. The rectangles should be bounded by the curves, okay? So in this particular case, we're going to draw a typical rectangle that looks like this. I check to make sure that f is always on top inside this region. It is. So the heights of every rectangle inside here are f of x minus g of x. I've got a consistent setup. My picture looks like I can apply the theorem directly. And so that means that I can conclude that the area of this entire region A is equal to the integral from a to b of f of x minus g of x dx. And the intuition that I want to take away from this formula is the a tells you the A tells you where to begin the region, right? Essentially what you should think of as this statement is saying is the integral sign means sum. You're adding things. The A tells you where to start adding, and the B tells you when to stop. The things that you're adding up are given by this formula right here. So f of x minus g of x is the height of a rectangle. The dx is the width of a rectangle. So the integral is telling you, start adding rectangles at A and go to B. And the rectangles that I want you to add have heights given by f minus g and widths given by dx. And you can see that in the picture. X minus A is where I start making rectangles. X minus B is where I finish. So essentially what the formula is telling you to do is take this region, chop, 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 chop into rectangles, estimate the area of each one, and then add those areas up, and you'll get an idea of what is inside here. The dx instead of delta x, because we're thinking of this as the infinitesimal version, which is really just a limit of approximations that come from the rectangles that are written right here. Okay, so the next part of this will just be examples. Thanks.